I was reading this report the other day about the sheer physical scale of the current AI boom.
Yeah.
And I wasn't looking at the code or the capabilities. I was looking at the plumbing.
The plumbing, you mean the physical reality behind the cloud.
Exactly, the infrastructure.
Right.
Because when we talk about this AI arms race, the mental image for you and me is almost always bigger is better.
Right.
We picture these trillion parameter behemoths, these massive data centers just humming out in the desert somewhere, consuming enough electricity to power a medium-sized European country.
Now, that has certainly been the dominant narrative in the space. It's what we call the scaling law dogma.
The scaling law dogma.
Right. Researchers like Kaplan famously plotted this out a few years ago. Basically, it's this idea that if you feed the beast more data and you give it more compute, intelligence just goes up and to the right.
Indefinitely.
Up and to the right. It's a very brute force approach.
Very brute force,
Yeah.
yes. But here's the twist. And it's really why I wanted to do a deep dive into this specific source material today. While all the headlines are screaming about the next, trillion parameter God model, there is a completely different race happening in the background.
Mm-hmm.
And in this race, the cutting edge is it's shrinking.
It is. We are definitely witnessing a pivot. We're entering the era of the small language model,
Right.
or SLM.
Right, because the goal here isn't to build a supercomputer that lives in some heavily guarded data center. It's to take that supercomputer and put it in your pocket.
On your phone?
On your phone. And crucially, without needing an internet connection to make it work.
Which is it's a radically different engineering challenge.
Yeah.
It's the difference between building a massive nuclear reactor to power a city and building a high-performance battery that fits inside a wristwatch.
That's a great way to put it.
You can't just take the reactor and shrink it down. You have to fundamentally rethink how you generate and store that energy.
So today we are diving deep into this comprehensive survey. It's simply titled A Survey of Small Language Models by Chien, and this massive collaboration of researchers.
Right, from the University of Oregon, Adobe Research, Meta AI, and several others. It's a very robust paper.
It's essentially the Bible for shrinking AI right now.
It really is a foundational text.
Mm-hmm.
And what I love about it is that it treats smallness not as a limitation, but as a feature.
A feature, yeah.
It builds a complete taxonomy, a classification system, really for what I like to call the dark arts of optimization.
The dark arts, I like that. So our mission today is to explore exactly how we go from these massive LLMs to SLMs. We're going to unpack techniques like pruning, quantization, and distillation.
And we'll also look at where these things actually live in the real world. Because the end game here isn't just to make a cheaper chatbot.
Right.
It's about running sophisticated, intelligent AI on edge devices. Mobile phones, smart glasses, things with very, very limited battery life.
Okay, so before we get into the actual surgery of how they slice up these models, we need to define our terms.
Sure.
What exactly counts as a small language model? Is there a strict cutoff, like you must be this short to ride the SLM ride?
It's surprisingly difficult to pin down because the definition of what is small and what is large is entirely relative to time. It's a moving target.
Okay, give me a benchmark so we can visualize it.
Let's take GPT-2.
But
When OpenAI released that back in 2019, it was the titan of its day. It had 1.5 billion parameters.
wow.
And people were genuinely terrified of it. There were actual serious debates in the community about whether it was too dangerous to release to the public because it could, write coherent paragraphs.
And today, where does that sit today?
Today, in the context of this survey we're looking at, 1.5 billion parameters is considered tiny.
Tiny.
Yeah, it's actually smaller than a lot of the models that are classified as small in current research. The survey generally looks at models that are designed to operate under strict hardware constraints.
So it's less about a rigid number.
Exactly. Though usually anything under about 7 billion parameters is in the ballpark. But it's really more about the intent behind the model.
The intent being its ability to survive on a constrained device, like a phone.
Precisely. And the source material highlights 4 main constraints that these SLMs have to solve for: latency, memory, privacy, and energy efficiency.
Let's break those down because I think latency is something we all feel every day, but maybe we don't actively analyze it.
Latency is just the wait time.
Yeah.
But on a phone, in a conversational interface, it's absolutely critical.
Right.
If you ask Siri or Google Assistant a question right now, it has to record your voice, package that audio, send it across the internet to a server farm in Virginia or wherever, process it through a massive model, and then send the audio answer all the way back.
And that whole round trip takes, what, 2 or 3 seconds?
2 or 3 seconds, yeah.
Which honestly feels like an absolute eternity when you're just standing there staring at your phone waiting for an answer.
It completely kills the flow of conversation. You can't have a natural back and forth with a 3-second delay. So an SLM running locally on the device needs to be instant. It needs to feel like a reflex, not a research project.
Makes sense. Okay, then there's memory.
Right. Your average smartphone has maybe 8 or 12 gigabytes of RAM total.
Okay.
If your AI model takes up 10 gigabytes of RAM just to exist in an active state, your phone is going to crash.
You literally wouldn't be able to open any other apps.
Exactly. You can't run Spotify. You can't run Google Maps. Your phone just becomes a very expensive, very hot brick.
Yeah.
So the model has to be small enough to live comfortably in the margins of your device's memory.
And energy. I mean, we all know the sheer panic of the 1% battery indicator.
Oh, absolutely. Running a transformer model is incredibly math heavy. It burns through CPU and GPU cycles like crazy.
So it generates heat and drains power.
Right. If talking to your AI assistant drains your phone battery from full to 0 in 20 minutes, nobody's ever going to use it. So when we say small, it isn't just a cute branding term. It's a strict engineering requirement for the device to even function.
Okay, so we know why we need them to be small. Now let's unpack how we actually build them. Because the paper seems to split this into 2 distinct schools of thought.
Yes.
School A says, let's design a brand new brain from scratch that is just naturally efficient. And School B says, let's take an existing big brain and compress it.
That's the core divide in the research right now.
Yeah.
Architecture versus compression.
Let's start with architecture. Section 1 of our deep dive, designing for smallness from day one. The paper talks about 2 main families of architecture here, encoder-only and decoder-only models. For those of us who aren't, deep learning engineers building these things every day, what is the practical difference between an encoder and a decoder?
Think of it like this. An encoder is really, really good at reading.
Reading, okay.
It takes a block of text, reads the whole thing, scrunches it down into a highly compressed mathematical summary, and really understands the deep context of it. It's fantastic for things like classification, sentiment analysis, or searching for a specific answer hidden inside a long document.
And this is the BERT family of models?
Exactly. BERT and its descendants.
Okay, so if encoders are readers, the decoder is.
The decoder is good at writing. Its entire job is to predict the next word in a sequence.
So that's your GPT, your llama model.
Yes. Most of the chatbots we actually interact with on a daily basis are decoder models because their primary function is to generate novel text back to us.
So if our ultimate goal is to put a smart chatbot on a phone, we're mostly looking at decoders. But the paper actually spends a good amount of time on the encoder evolution first, specifically a model called MobileBERT.
Yeah, MobileBERT is a really classic case study in efficiency. They achieved a massive reduction in size by using something called an inverted bottleneck structure.
Okay, an inverted bottleneck. I'm going to be honest, that sounds like a plumbing problem you have to call a very expensive specialist to fix.
It really does sound like that. But try to visualize a neural network as a series of pipes passing water, which represents the data through the system.
Okay, I'm picturing the pipes.
In a standard model, like the original BERT model, the pipes are just wide all the way through. You have these massive, thick layers holding lots of information at every stage.
So big pipes, lots of water flowing through constantly.
Right, it's very high capacity,
Yeah.
but it's incredibly slow and heavy on memory. Now, in a traditional bottleneck architecture, you squeeze the data down into a very narrow pipe to process it, and then expand it back out.
To save space.
Exactly. But MobileBERT inverted that logic. They realized that the really complex math, the actual thinking the model does, needs room to breathe. So they keep the data compressed. They keep the pipe narrow when the data is just moving between layers to save on transport memory.
Yeah.
But right when they need to do a heavy calculation, they project that data into a high-dimensional space, a really wide pipe, do the math almost instantly, and then immediately squeeze it back down for the next stage of transport.
So it's kind of like, it's like efficient packing for a winter trip. You keep all your bulky clothes vacuum sealed in your suitcase to save space while you're traveling. That's the transport.
Yes.
And you only rip open the vacuum bag and expand that big puffy winter coat when you actually step outside into the snow and need to wear it, the calculation.
That is a fantastic analogy. Exactly. You don't walk through the airport wearing 5 heavy winter coats just in case.
Yeah.
You pack them away. MobileBERT used this exact philosophy to become 4.3 times smaller and 5.5 times faster than the original BERT model.
And that speed difference, 5.5 times faster when we're talking about real-world usage, that is the difference between a user waiting a full second versus getting a totally instant response.
Precisely. It crosses the threshold into feeling real-time. And then you also have models like DistillBERT, which manages to retain about 97% of BERT's performance while being significantly lighter.
It's amazing how much fat there is to trim.
It is. But you're right, the real buzz lately, especially for consumer applications, is on the decoder side. The GPT and Llama style models.
The ones we actually chat with.
Yes. And here, the survey highlights models like TinyLlama and MobileLM. TinyLlama is fascinating because it manages to pack 1.1 billion parameters, but it's heavily optimized with a technique called flash attention to handle the memory overhead during processing.
Now, speaking of MobileM, the survey also mentioned it uses something called embedding sharing. The authors made a pretty big deal out of this specific trick. What exactly is it?
No, it's okay. So every single language model has a vocabulary, a massive list of maybe 50,000 or 100,000 tokens, which are words and parts of words. This is called the embedding table.
So it's a dictionary.
It's basically a massive dictionary that maps our human words to mathematical numbers the computer can understand.
And I'm guessing this dictionary takes up a lot of space on the hard drive.
A huge amount of space. Now, in massive models with hundreds of billions of parameters, the dictionary is just a tiny fraction of the total size. You don't even notice it.
Right.
But when you start shrinking the model down to build an SLM, the dictionary doesn't shrink. It still needs to know all the words. So suddenly the dictionary alone can make up 20% or even 30% of the total parameter count of the model.
That's a massive footprint just for the vocabulary.
It is. Now, traditionally, a standard model actually has two dictionaries. It has an input dictionary to understand what you just typed to it, and a separate output dictionary to decode its math back into words to show you.
Wait, why would it have two?
Well, historically, it gave the model a bit more flexibility during training, but MobileM looks at that and asks, why do we have two identical dictionaries?
Right, why buy two copies of the Oxford English Dictionary to keep on the same desk?
Exactly, so they just share them. By tying the input and output embeddings together so they reference the exact same table, you instantly shave off a huge chunk of memory usage without really hurting the model's performance at all.
It's such an elegant, low-hanging fruit solution.
It really is. It's crucial for getting these things onto mobile devices.
Smart. But as we dig deeper into the architecture, there's a much bigger math problem lurking here, isn't there? The paper calls it the self-attention bottleneck. And they mention this term, ON squared complexity. Now, I see that and my eyes immediately glaze over, but I know it's the core of the issue.
It is the single biggest barrier to having long conversations with AI. Let me try to explain it without bringing in the calculus.
Please do.
Imagine you are at a small cocktail party, just you and 9 other people in a room.
Okay, 10 people total, cocktail party.
If you want to really understand the deep social dynamic of that room, who is secretly angry at who is flirting, you have to carefully watch every single interaction. You watch person A talking to person B, then person A to person C, then person B and person C.
Okay, with 10 people, that's entirely manageable. I can track that.
Now imagine you are standing in the middle of a massive sports stadium with 10,000 people.
Oh, boy.
If you have to track every single person's interaction with every other person in that stadium, the number of connections doesn't just go up a little bit, it explodes. It's not 10,000 connections, it's 10,000 squared.
Which is 100 million connects.
Exactly. That is quadratic complexity. That's the n squared.
And in this analogy, the people in the stadium are the words in our chat.
Yes. In a standard transformer model, if I write a paragraph, the AI compares every single word to every other word to fully grasp the context.
To see how they all relate to each other.
Right. But if I paste a whole book into the chat window, the number of mathematical comparisons becomes astronomical. The memory required to hold all those comparisons spikes, the processing speed slows to an absolute crawl, and if you're on a phone, your battery dies instantly.
So standard transformers, like the big GPT-4 models, they're just inherently stuck with this quadratic math.
Mostly, yes. They just throw massive amounts of cloud computing power at the n squared problem to solve it. But for SLMs, we don't have infinite cloud compute. We need to break that law.
We need a workaround.
We need what they call linear attention. We want ON, linear complexity, meaning if you double the number of words in the prompt, you only double the work the computer has to do. You don't quadruple it.
How is that even possible if you still need to understand the context of the whole document?
This is where we start getting into the really exotic experimental architectures. The survey highlights two major breakthroughs here, Mamba and RWKV.
I've actually been hearing a lot of buzz about Mamba lately online. It sounds cool, but what is the actual secret sauce there?
Mamba is fascinating because it moves away from the pure transformer architecture entirely. It uses something called selective state space models, or SSMs.
State space models.
Think of the difference between a transformer and Mamba, like the difference between a massive research library and a conveyor belt.
Okay, I'm with you. Go on.
In a standard transformer of the library, the model basically keeps every single book you've ever mentioned open on the table all at once. Every time it reads a new word, it looks back at every single open page to check the context.
That's the n squared problem, constantly looking backward at everything.
Exactly. Mamba, on the other hand, is the conveyor belt. It reads the text much more like a human reads a book word by word, moving from left to right.
Right.
But it has this hidden state, a highly compressed running memory of what it just read. And as it moves along the conveyor belt, it dynamically updates that memory. It decides in the moment what is important enough to keep and what is useless filler it can forget.
Oh, wow. So it's actively filtering. It doesn't need to look back at page one constantly because it already compressed the important facts from page one into its running memory state.
Precisely. It brings the relevant info along with it. This means the memory usage stays constant no matter how long the book you feed it is. It's incredibly fast and lightweight for inference on a phone.
I mean, that sounds superior in every possible way. Why aren't we just using Mamba for every single AI model right now?
Because transformers are still slightly better at one specific thing. Random access recall.
Meaning what?
Meaning, if the answer to your prompt depends heavily on one incredibly specific, obscure word hidden 50 pages ago in a massive document, a transformer can look right at it because it kept the book open.
But Mamba might have discarded it.
Right. Mamba has to rely on having correctly guessed that that word was important enough to compress into its state memory an hour ago.
Got it.
But for a conversational chatbot on a phone, where you're just asking for a recipe or a quick summary, Mamba is a total game changer.
And the other one you mentioned? RWKV.
RWKV is a really clever attempt to marry two different worlds of AI history. It combines recurrent neural networks, RNNs, which are very old school, very fast, and very light, with modern transformers, which are very smart but heavy.
So it's a hybrid.
Yeah. The goal is to get the lightning-fast inference speed of an RNN, but keep the parallel training capabilities of a transformer. And these models actually achieve that linear complexity, making them incredibly viable for edge devices.
So that's all about designing the brain perfectly from scratch, figuring out the exact right blueprint. But what if we don't know what the perfect blueprint looks like for a specific task?
Then we use AI to design the AI.
Which sounds very sci-fi.
It does. It's a field called Neural Architecture Search, or NAS.
So instead of a human architect sitting down and drawing out the network blueprint, how many layers, how many connections, we just unleash an algorithm to test millions of variations.
Exactly. Mobile LM use NAS extensively. Instead of guessing how deep the model should be, the number of layers, or how wide it should be, the number of neurons per layer, they ran a massive automated search.
And what did they find?
They found the mathematical sweet spot. And it turns out that for small models, the ideal trade-off between depth and width is actually very different than the architecture you'd use for a massive GPT-4 style model. You can't just scale it down proportionally. The internal proportions have to change.
Okay, so we've built this sleek, naturally efficient architecture, but sometimes even the best architecture is still just too big to fit on a watch or a phone. We need to actively compress it.
Right.
Which brings us to section 2 of the deep dive. Pruning.
Pruning, the art deletion.
This concept actually fascinates me because it implies that our cutting-edge AI models are actually lazy.
They are incredibly lazy. It's a recognized concept. We actually call it the lazy neuron phenomenon.
Explain that to me. How can a math equation be lazy?
Well, when you train a massive language model, you give it billions and billions of parameters, these mathematical connections between artificial neurons to work with.
Yeah.
You give it a huge brain to solve problems.
But
it turns out the model doesn't really use all of them. During training, it finds a few really strong, reliable pathways to route the data and solve the problems you give it. And the rest of the connections, they just sit there. Their mathematical values drop to 0 or near 0.
They aren't contributing to the final answer at all?
They're pure dead weight. Pruning is simply the algorithmic process of identifying those lazy deadweight neurons and cutting them completely out of the model to save space.
Which sounds simple in theory, But how do you know which ones to cut without accidentally giving the AI a lobotomy and ruining its ability to think?
That is the trillion-dollar question in compression. And the survey breaks down two main approaches to solving it: unstructured pruning and structured pruning.
Let's start with unstructured.
Unstructured pruning is like going through the neural network with a very tiny scalpel and removing individual connections, individual weights that have very low mathematical values.
Yeah.
You aren't removing whole neurons or whole layers, just specific tiny connections scattered everywhere that seem irrelevant.
The survey mentioned a tool called Sparse GPT for this.
Yes, sparse GPT is a huge milestone because it formulates the pruning process as a mathematical regression problem. It can take a massive open source model like Bloom 176B, which is huge, and prune it in one shot.
Meaning what?
Meaning it doesn't need a long, expensive retraining process to heal the AI's brain after the surgery. It just calculates the optimal cuts and makes them, and the model still works.
That's impressive. And there was a newer technique mentioned too, right? Wanda?
Yes, Wanda is really interesting because traditional pruning just looks at the static weight the number saved on the hard drive.
Right.
Wanda says, that's not enough. It looks at the weight and it also looks at the activation, meaning it looks at the actual input data flowing through that connection when the model is running.
So it's observing it in action.
Exactly. It asks, is this weight important given the actual data we normally see? And it can make those cuts dynamically without needing to retrain the model at all.
That sounds perfect. But I recall this survey pointing out a pretty major catch with unstructured pruning. They called it the Swiss cheese problem.
Ah, yes. The Swiss cheese problem.
Yeah.
This is where software hits the wall of hardware. See, when you randomly poke millions of tiny holes in your matrix of numbers by deleting individual weights here and there, you end up with what mathematicians call a sparse matrix.
Which looks like Swiss cheese. Lots of holes.
Exactly. And the problem is that standard computer hardware, specifically the GPUs that run AI, they absolutely hate Swiss cheese.
Why?
Because GPUs are designed to process dense, solid blocks of data. They like to grab a huge, solid chunk of memory, run a massive calculation on it all at once, and move on.
So if there are random holes scattered everywhere.
The GPU essentially has to pause and check every single spot. Is this a number or is it a hole? Okay, calculate the number. Next one, is this a number? No, it's a hole. Skip it.
And all that checking takes time.
It ruins the efficiency. So even if you successfully remove 50% of the weights from the file, if they are scattered completely randomly, your phone might not actually run the AI any faster.
So you made the file size smaller on the hard drive, but you didn't actually make the thinking process any faster.
Precisely. Which leads us to the second approach, structured pruning.
And this is where you remove whole groups of things instead of individual connections.
Right. Instead of picking tiny crumbs out of the cake, you cut out a whole clean slice. You remove an entire neuron or an entire channel or sometimes an entire layer of the network.
Which keeps the remaining block of data solid.
Right. It maintains the dense structure so the GPU hardware stays happy and runs at maximum speed. There's some really cool, very specific techniques here. One that's very popular right now is the NM strategy, which NVIDIA heavily promotes.
NM. What does that stand for?
It stands for N out of M.
Ah.
So a common one is 2.4 sparsity.
Okay, 2.4.
It means that for every solid block of 4 consecutive weights in the matrix, you strictly enforce that exactly 2 of them must be pruned to 0.
So it's a very predictable, repeating pattern of holes.
Exactly. It's a compromise. It's structured and predictable enough that specialized hardware, like NVIDIA's TensorArt, can actually optimize for it and skip the holes instantly, but it's flexible enough that you can still prune the model effectively without ruining its intelligence.
Okay, that makes sense. And there was another concept in this section that sounded almost like magic to me. Contextual sparsity.
Ah, you're talking about déjà vu.
Déjà vu, yes.
That's the name of the method. And it's brilliant because it's dynamic. See, standard pruning deletes the weights permanently. They're gone from the hard drive forever.
Right.
Déjà vu challenges that core assumption. It asks, why permanently delete them? Why not just put them to sleep when we don't need them?
Go on.
Think about the human brain for a second. If I ask you to solve a complex calculus problem, you activate the math and logic centers of your brain.
Hopefully, yes.
You are not actively using the part of your brain that knows how to cook spaghetti, or the part that remembers the lyrics to an 80s pop song.
No, that would be very distracting.
Exactly. Déjà vu tries to replicate that biological efficiency. It leaves the entire model completely intact on the hard drive. Nothing is deleted. But it uses a tiny, hyper-fast predictor mechanism to look at your prompt.
Okay.
It says, oh, the user's asking a question about writing Python code. And it instantly only activates the specific pathways in the network that deal with coding. It ignores the poetry pathways, it ignores the French translation pathways, it creates sparsity on the fly in real time.
That makes so much sense. Why force the computer to load the 18th century poetry module into RAM if I'm just trying to do calculus?
Precisely. It saves massive amounts of memory bandwidth during inference. And finally, on the extreme end of structured pruning, some research suggests you can just be completely ruthless and drop entire layers of the model.
Like just delete an entire floor of the building.
Yeah, because transformers are actually very repetitive by nature. The survey cites work by Sajjad and others showing that sometimes layer 11 and layer 12 in a deep model are doing almost the exact same mathematical transformation.
So you just delete layer 12.
You just delete it. And the model barely even notices it's gone, but it runs significantly faster.
Ruthless efficiency. I love it. Okay, moving on to the next major dark art of compression, quantization.
Quantization.
Yeah.
This one is honestly my favorite because it's so counterintuitive that it even works at all.
This is where we get into the pixel art analogy, right?
Yes. So a standard uncompressed AI model stores all of its numbers, its billions of weights, as 32-bit floating point numbers.
Okay, 32-bit floating point.
Think of that as a high-definition 4K photograph. It's a number with a massive amount of decimal places for extreme precision, like 3.141599265, and so on, forever.
High resolution.
Super high res. Quantization is the engineering process of looking at that and asking, do we really truly need all those decimal places to know it's roughly the number 3?
Right.
Or do we just round it? What do we round it to 3.1? Or just the whole number 3? We mathematically round those massive 2-bit floating points down to 8-bit integers, or even 4-bit integers.
So you're taking that beautiful 4K high-res photo and you're intentionally crunching it down into a blocky 8-bit Nintendo character.
Yes, exactly. And the hope, the gamble, really is that you can still recognize what the image is supposed to be, but the memory savings are immediate and massive. Just going from 32-bit to 4-bit is an 8x reduction in file size, instantly.
That's how you fit a 7 billion parameter model onto a smartphone's RAM.
That is exactly how you do it.
But wait, surely you lose intelligence, right? If I'm building a bridge and I round 3.14 down to just 3 in my math, my bridge is going to collapse.
You definitely lose mathematical precision, yes.
Yeah.
But surprisingly, you lose very little actual intelligence if you do the quantization intelligently.
Why is that?
Because neural networks don't work like calculators. They work on broad statistical probabilities and massive overarching patterns. They are incredibly robust to a little bit of noise or rounding errors in the individual number.
Oh, that makes sense.
However, there is a catch. There is always a catch in optimization.
Let's hear the catch.
The paper calls it the outlier problem.
The outlier problem, and this has to do with activations, right?
Right. So we just talked about rounding off the weights, which is the static memory of the model sitting on the hard drive. That's relatively easy because they don't change. A technique called GPTQ is the absolute gold standard for weight-only quantization right now.
Okay, so weights are easy.
But the activations, those are the numbers that represent the actual data flowing through the model when you ask it a question in real time.
Yeah.
Those numbers change every single millisecond. And sometimes they randomly spike.
Massively.
Give me a visual for this spike.
Okay, imagine you are trying to fit a highly detailed topographic 3D map of the entire world into a small, flat shipping box.
Okay. Map in a box.
Most of the land on Earth is at or near sea level. It's relatively flat. It's very easy to fit the flat parts into the box. But suddenly you have Mount Everest, a massive, towering outlier.
And if I set the lid of my box high enough to fit Mount Everest without crushing it, there's going to be a huge amount of empty, wasted space above all the flat land. Exactly. And in quantization, you only have 4 bits of very small box to represent the entire scale. So if you squash Mount Everest down to fit the box, you have to scale everything else down proportionally.
Which means all the subtle valleys and small hills just get flattened into zero. They vanish.
You lose all the vital detail of the normal signals. This is exactly what happens in activation quantization. A few neurons just scream. They have massive, unpredictable mathematical values. If you try to force those outliers into a tiny 4-bit integer scale, you destroy the mathematical information in all the normal, quiet neurons.
So the model gets stupid. How do we deal with Mount Everest then? The survey mentioned 2 specific solutions here, smooth quant and spin quant.
Smooth quant is a very clever mathematical trick. It shifts the difficulty around. It basically smooths out those unpredictable activation spikes by taking some of their mathematical weight and pushing it into the static weights of the model instead.
Because the static weights are easier to round off.
Exactly. It effectively flattens Mount Everest before you even try to put it in the box.
And what about spin quant? That one sounded like a weird geometry class to me.
It literally is geometry. Spin quant rotates the matrix.
It rotates the math. What does that even mean?
Yes, it uses literal rotation matrices from linear algebra to take the data and spin it into a completely different geometric coordinate space. And in this new rotated space, the massive outliers are mathematically spread out and much more manageable.
It's like if you have a really weirdly shaped tall lamp and it won't fit through the door vertically, you just tilt the box sideways so it fits.
That is exactly what it is. You just rotate the math to make it fit through the 4-bit door. It is wild engineering.
That is incredible.
And it works beautifully. It allows us to run these powerful models at 4-bit precision with almost zero noticeable loss in conversational performance.
Amazing. Now, there was one more piece of quantization specifically related to memory that I want to make sure we hit. The KV cache. We need to explain that because it sounds very technical, but it's actually crucial for anyone who just wants to chat with an AI.
Ah, yes. KVI. This is a very specific, crucial technique for long context.
Because when you talk to a chatbot, it has to remember what you said 5 minutes ago, right?
Right. And that running memory of the conversation is stored in something called the key value cache, the KV cache.
It's like a running cheat sheet of the chat.
Exactly. But as your conversation gets longer and longer, that cheat sheet gets huge. I'm talking gigabytes of valuable RAM on your phone, just consumed to remember that you said hello and asked about a recipe 20 minutes ago.
Which brings us back to the memory constraint crashing the phone.
Right. So KVI is a framework that allows us to heavily quantize, to compress that specific KV cache. It compresses the memory of the conversation itself on the fly, so you can have hour-long deep chats with an SLM on a device that only has a few gigabytes of RAM.
Okay, so to recap, we've designed an efficient brain. We've pruned the dead weight out of the brain. We've pixelated the math to shrink it down. Now let's talk about how we actually put knowledge into it. Section 4, knowledge distillation.
The teacher and the student.
This is the concept that we can use a massive trillion parameter LLM like a GPT-4 or a Claude to directly teach a tiny blank slate SLM.
Correct. And this is a huge shift because usually models learn by reading raw data, scraping Wikipedia, reading Reddit, scanning the whole internet.
Which takes months and massive compute.
And raw data is messy. It's full of typos, contradictions, and noise. It's very hard for a small model to learn from scratch. So in distillation, the SLM, the student, doesn't look at the messy internet. It only tries to mimic the refined output of the LLM, the teacher.
So the teacher AI digests the messy internet, understands it, and then explains it simply to the student AI.
In a way, yes. The teacher provides what we call soft labels.
Sharp labels.
Let's say we are training a model to recognize animals. If it's just learning from raw data, the data gives a hard label. It points to a picture and says, this is a cat, 100%.
Okay.
But a teacher model looks at that same picture and provides a soft label. It says, okay, there's a 90% chance this is a cat, but it has pointy ears, so there's a 5% chance it's a fox, and maybe a 5% chance it's a small dog.
Oh, I see.
That extra nuance, those probabilities about what it almost looks like, that contains so much more underlying information about the structure of reality. And it helps the small student model learn the actual concepts much, much faster.
The survey mentioned a model called Baby Llama in this section.
Yes. Baby Llama is fascinating. It's a 58 million parameter model.
That is tiny. That's microscopic in AI terms.
It really is. And it was distilled directly from a much larger llama model. The really surprising finding there was that this tiny distilled student actually outperformed another model the exact same size that was trained from scratch on the original data.
Wow. So learning from the teacher is literally better than reading the textbook yourself.
Because the teacher acts as a filter. It cleans up the noise and highlights the important patterns.
But when it comes to really complex tasks, it's not just about copying the final answer, is it? It's about copying the logic.
That is exactly the new frontier right now. It's called reasoning distillation, or chain of thought distillation.
Right, because if I'm taking a math test and I just lean over and copy your final answer, I get an A on the test, but I didn't actually learn how to do the math.
Exactly. If the teacher model just spits out the answer 42, the student learns absolutely nothing about the underlying mathematical process.
It just memorizes 42.
Right. So in chain of thought distillation, we've forced the teacher to generate the step-by-step logic out loud. First, I add these two numbers. Then I carry the 1. Then I divide by x. Therefore, the final answer is 42.
And the student reads that whole paragraph.
The student learns to mimic the intermediate steps, not just the destination.
And the survey indicates this is a huge deal for things like arithmetic and coding, right?
Massive. The paper cites work by Chien and others showing that this technique dramatically improves arithmetic and symbolic reasoning in small models. You can make a tiny model surprisingly good at complex math if you spend the time to teach it how to think, rather than just what to say.
This transitions perfectly into how we actually handle the logistics of training these things. Section 5. Because even for an SLM, training from scratch is expensive.
Incredibly expensive. It requires vast arrays of GPUs running for weeks.
So what are the industry tricks to doing it on a budget?
Well, first, we have mixed precision training. We touched on the idea of precision with quantization, but this is applying it to the training phase.
Okay.
During training, instead of doing all the heavy calculus using massive 32-bit numbers, we use lower precision numbers like FP16 or bfloat16 to do the rapid calculations. This saves a ton of memory and speeds up the math.
But doesn't that make the training inaccurate?
We keep a high-precision master copy of the weights stored safely to the side, and we update that master copy with the results of the fast, low-precision math. The new NVIDIA Hopper architecture even natively supports FP8 8-bit floating point, specifically for speeding up this training process.
Very cool. But what if the model, even an SLM, is still too big to physically fit into the memory of a single training GPU?
Then you have to shatter it. This brings us to distributed training frameworks. Techniques like ZERO, which stands for Zero Redundancy Data Parallelism, and FSDP, Fully Sharded Data Parallel.
Fully sharded sounds very intense.
It is a massive orchestration challenge. Imagine you have a model that needs 40 gigabytes of RAM, but your GPUs only have 16 gigabytes each.
It won't fit.
Instead of forcing every single GPU to hold a full, complete copy of the model, which is the old way of doing it, you break the model down into shards, little pieces.
And you spread them out.
You spread the shards across hundreds of different GPUs working in parallel. No single chip has the whole brain. They communicate constantly over high-speed networks to sync up their calculations. It allows you to train models that are physically impossible to fit on one machine.
Okay, so let's say we've done all that. We've successfully pre-trained our base SLM. It knows English, it knows basic facts, but now I want to customize it. I want my personal SLM to be an absolute world-class expert in, I don't know, 18th century French poetry.
Okay, niche, but sure.
But I don't want to spend $1 million on server time retraining the entire model from scratch just to teach it poetry.
You definitely don't have to. Enter PEFT, Parameter Efficient Fine-Tuning. And the absolute star of the show in this space is LoRa, low-rank adaptation.
I feel like I hear LoRa mentioned everywhere right now, every paper, every forum. What is the best way to visualize how LoRa works?
Okay, imagine your pre-trained base model, one that knows general English, is a massive, heavy, beautifully bound, sealed textbook. It has all the general knowledge in the world inside it.
I'm picturing it.
But the rule is you are absolutely not allowed to take a pen and write in the textbook. You cannot permanently alter the pages.
Okay, the textbook is frozen.
LoRa is the equivalent of taking a tiny stack of translucent sticky notes and just placing them on specific pages of the textbook.
Sticky notes.
Yes. You completely freeze the main model, you don't touch those billions of parameters, and you just train this tiny little adapter layer. That's the sticky note. It sits on top of the model and slightly alters how it reads the page underneath it.
So the sticky note has my French poetry knowledge on it.
Exactly. And the brilliant part is, the LoRa adapter is tiny. It's maybe 1% or even 0.1% of the size of the base model. You can train a LoRa on a single consumer graphics card in an afternoon.
So when I want my chatbot to switch from analyzing French poetry to writing Python code, I don't need a whole new textbook. I just peel off the poetry sticky notes and slap on the Python sticky notes.
Exactly. You keep the exact same heavy base brain loaded in RAM, and you just swap out these tiny megabyte-sized adapter files.
The survey also mentioned something called LoRa switch.
Right. That takes the sticky note concept a step further into full automation. It uses a mixture of experts approach.
Explain that.
Imagine you have a huge binder full of hundreds of different sets of sticky notes. One for math, one for poetry, one for legal documents, one for coding. LoRa Switch dynamically evaluates what you are asking it, and in real time, it swaps the correct adapters in and out to answer that specific prompt optimally.
That is brilliant. It just adapts its expertise instantly. Now, to train those sticky notes, we need good data. And if we are training a small model, the quality of that data has to be pristine.
Yes. And paradoxically, the absolute best source of high-quality training data for small models is the massive, big models.
We're back to using ChatGPT to write the textbook for the baby AI.
Yes, it's called data augmentation. Techniques like AuGPT use massive LLMs to constantly rephrase and rewrite existing data to create more grammatical variety for the small model to learn from.
And there was another one, Evil Instruct.
Evil Instruct is really cool. It takes a very simple, basic instruction, and it uses a huge LLM to intentionally make it more complex. It adds constraints, it makes the logic harder, it introduces nuance.
So it's actively challenging the small model.
It creates a customized, high-difficulty gem for the small model to work out in. And this is incredibly crucial for low-resource domains. Like trying to train an SLM to speak a rare indigenous language or understand highly specific medical imagery, where we simply don't have millions of human-written documents available to train on. The LLM hallucinates highly accurate synthetic data to fill the gap.
Okay, so we have the tech, we have the training pipelines, we have our sticky notes. Let's talk about the real world, Section 6, applications. Where do these SLMs actually live right now?
The most obvious massive deployment happening right now is on the device you are probably holding, mobile.
Apple is obviously making massive moves here.
Huge moves. The survey specifically points out Apple Intelligence. They built a roughly 3 billion parameter on-device model that handles all your text summarization, your email drafting, your code completion.
And it does it entirely locally.
Entirely offline,
Oh.
without sending your personal emails to a server.
And on the Android side?
Android is pushing Gemini Nano natively into their OS. And a really incredible, tangible example of the real-world benefit of this is Google's TalkBack feature for blind and low vision users.
How does that work in practice?
TalkBack uses the local SLM to provide incredibly detailed audio descriptions of images on the screen, completely offline.
Okay, imagine a scenario.
Imagine a blind user is navigating a deep, underground subway station. There's zero cell signal, no Wi-Fi. They point their phone camera at a complex transit sign or an unexpected obstacle.
If that relied on a cloud-based AI, it would just fail. It would time out.
It would fail completely when they need it most. But because Gemini Nano is an SLM running locally on the phone's hardware, it works instantly, anywhere. That is a literal life changer for accessibility.
That is the perfect argument for SLMs right there. And what about general performance for these mobile models? Can they compete?
Definitely. MobileLM, which we talked about earlier with the shared dictionaries, actually achieves benchmark performance comparable to Llama 2.7b, which is a significantly larger model, but it runs natively on standard mobile chips.
Then there is the real-time interaction space. I have to say, my biggest pet peeve with voice assistants is the lag. You ask a question, you wait 2 awkward seconds, it finally answers. It ruins the illusion.
The cloud round trip kills the illusion. SLMs solve that entirely. The survey mentions a model called Llama Omni, which is specifically designed for end-to-end speech interaction with extremely low latency.
End-to-end speech, meaning it doesn't translate it to text first.
Exactly. It cuts out the middleman. Normally it goes audio to text to the AI brain, back to text, back to audio. Llama Omni just ingests the raw audio wave, thinks, and outputs an audio wave. It is blazingly fast.
And Google has Project Astra.
Project Astra is incredible because it's multimodal. It's processing live, continuous video and audio feeds from a pair of smart glasses or a phone camera and lets you interact with the world.
Like, where did I leave my keys?
Where are my keys? Or you point the camera to a whiteboard and say, explain this math problem. It absolutely has to be an SLM running locally because streaming continuous high-res video to the cloud for real-time analysis would introduce massive lag and eat your data plan alive.
That brings up VR and mixed reality. Because if you have lag in a VR headset, you don't just get annoyed, you get physically motion sick.
Exactly. If the frame rate drops below 90 frames per second, the user throws up. It's a hard limit.
So you can't have a giant AI hogging the processor.
Right. So they highlight systems like LLMR, which uses highly optimized SLMs to instantly generate and modify complex 3D scenes based on voice commands without dropping frames.
And Dreamcode VR.
Dreamcode VR allows developers to actually write and debug code inside a virtual reality environment, using natural voice commands, parsed locally by an SLM so it feels instantaneous.
And finally, in this section, they touch on edge computing. We're talking really tiny devices here, Raspberry Pis.
The tiny ML space.
Yeah.
The paper highlights a project called EdgeMo.
MoE, mixture of experts.
Yes. They actually figured out how to run complex mixture of experts models on tiny, low-power devices like a Raspberry Pi or an NVIDIA Jetson.
What's the application for that?
It brings real intelligence to the absolute edges of the network. security cameras that can identify specific threats locally without streaming video to the cloud, agricultural drones that analyze crop health in real time over a field with no internet, industrial robots making split-second safety decisions locally.
Okay, it all sounds very utopian. Fast, private, efficient. But we have to be realists here. Let's move to Section 7, the trade-offs and open problems. Because there is no free lunch in engineering.
No, there is not. Smaller is absolutely not always perfect.
Let's tackle the big one first, hallucinations. Do small models make things up more often than the big ones?
It's a really complex issue. Your intuition would tell you that a dumb, small model lies more. And generally, on broad knowledge benchmarks like HallusionBench, the larger models do hallucinate less simply because they have physically memorized more world knowledge to draw from.
They've literally read more books, so they know the facts.
Right. But
Yeah.
there is a really counterintuitive finding with the Llama series that the survey points out. As the parameter count increased, as the model got bigger and theoretically smarter, its systemic bias actually increased.
Really? Why would it get more biased?
Because a massive model has absorbed so much more of the internet. And the internet is full of human prejudice, stereotypes, and toxic patterns. The bigger model internalized all of that.
So the small model is actually less prejudiced.
Sometimes, yes. And furthermore, smaller models are often much less prone to a specific type of hallucination regarding faithfulness.
Faithfulness, what does that mean in this context?
Faithfulness is the model's ability to strictly stick to the prompt you gave it.
Right.
If I give an AI a short news article and say, summarize only the facts in this text, a massive, highly creative, large model might actually drift off and inject outside information it memorized about that topic from Wikipedia.
Which technically breaks the rule of summarizing only the text.
Exactly. A small model, being much less imaginative and having less outside knowledge, often sticks much closer to the literal instructions. It is more faithful to the text. It's more obedient.
That's fascinating. So for highly constrained specific tasks, an SLM might actually be more trustworthy.
Yes.
Okay, what about energy? We spent all this time saying SLMs are energy efficient. But is there a catch?
They are very efficient per token generated. The math takes less power. But the single biggest predictor of energy consumption isn't actually the size of the model. It's the length of the response it generates.
Oh.
If you ask your highly optimized SLM a simple question, and it is overly chatty and generates 3 massive paragraphs of rambling text to answer you, it is going to drain your phone battery just as fast as a slightly larger model that just gives you a concise one-sentence answer.
So verbosity is the enemy of battery life.
Brevity is battery life. We have to train these SLMs to be concise.
And finally, privacy. We keep saying that on-device AI is fundamentally more private because your data never leaves the phone.
It is much more private regarding network interception, yes. You completely eliminate the man-in-the-middle attack. Your photos don't sit on a corporate server. But an on-device model physically resides on your device.
So if I leave my phone on a park bench and a hacker steals it?
If an attacker gets physical access to the device or manages to install malware, they can attack the AI model directly. And the survey warns about prompt leaking.
What is that?
It's where the attacker uses clever inputs to trick the model into spitting out its hidden system instructions. Or worse, if the model accidentally memorized sensitive information during its training phase, a local attacker can probe it millions of times offline to extract that training data.
Because they have unlimited offline attempts. They aren't blocked by a cloud server rate limit.
Exactly. It's a completely different threat model that security researchers are just now figuring out how to defend against.
Wow. Okay, so we've covered a massive amount of ground today. From the inverted bottlenecks of Mobile BERT to the conveyor belt of Mamba.
We've explored the Swiss cheese of unstructured pruning and the pixelated math of quantization.
It really feels like a complete philosophical shift in the industry. We are rapidly moving away from this era where one giant God model rules all into this highly specialized, highly distributed ecosystem of small, nimble models.
It's exactly like the shift in the 1980s.
Yeah.
We're moving from the era of the giant, centralized mainframe computer that you access remotely to the era of the personal computer sitting on your desk.
That's a perfect analogy. And this dark arts toolkit we discussed, the pruning, the quantization, the distillation, that is the engineering that makes AI ubiquitous. It's what is going to put a supercomputer in your car dashboard, your smart glasses, your watch, and maybe even your toaster eventually.
Probably your toaster, yes.
But before we sign off, I want to leave you, the listener, with a final, slightly provocative thought that builds on everything we just discussed. We talked a lot about the mixture of experts concept.
Right. The binder of sticky notes.
And we talked about distillation, where the teacher AI trains the student. When you put those two concepts together, are we inevitably moving toward a near future where a massive cloud-based teacher AI, the mothership, spawns billions of highly specialized student AIs that live on our devices?
I think we absolutely are. Picture it. You have a unique student AI that lives entirely on your phone.
Okay.
It observes you. It learns your daily schedule. It learns your specific email writing style. It learns your reading preferences.
And it does this using what the survey mentioned briefly, federated learning.
Yes.
So,
Using frameworks like A. Federated learning allows the model to analyze your private data, extract the mathematical lessons from it, and update its own brain without your actual text messages or photos ever leaving your pocket.
and it only ever calls home to the mothership when it hits a wall.
Exactly. Hey, teacher AI, I don't know how to solve this incredibly complex physics problem my user just asked.
Yeah.
The massive cloud teacher solves it, explains the logic to the student learns how to do it for next time, and the connection closes.
It's a truly personalized, perfectly private, distributed intelligence network.
Which, if you think about it, is infinitely more useful and, frankly, much safer than just having one giant omniscient chatbot sitting in a corporate data center somewhere reading all of our emails.
I completely agree. It puts the actual ownership of the intelligence back into the user's hands.
It democratizes the capability.
So next time your phone downloads a massive operating system update, take a second to appreciate the tiny, highly optimized artificial brain that just moved into your pocket. It might be small, but it is dense with absolute engineering wizardry.
It's small, but it's mighty.
Thanks for joining us on this deep dive. We'll catch you next time.
Goodbye.